Okay, last lesson we talked about these identities. We talked about how to use them. We proved them using basic trigonometric identities. Sine is equal to opposite over hypotenuse, etc. Today we're going to look at that and go the next step further. How do we prove the further identities based upon these 7 or 8 basic ones that we already know? So we are going to use deductive reasoning to do that. And basically deductive reasoning is taking facts we already know and applying them to something that we want. So we already know that these 8 identities are true. We can use them for anything. There are 4 steps. The first one is to check to make sure the teacher isn't messing with you, i.e. check to make sure that this could possibly be an identity in 2 ways. The first one is verifying using a particular number. I'm going to use pi over 3 because it's a special triangle angle, and I can use my exact values from my special triangle. So I want to see if 1 over cos pi over 3 minus cosine pi over 3 is the same as if I go sine of pi over 3 times tangent of pi over 3. So tangent is opposite over adjacent. So pi over 3, that's square root 3 over 1. Sine is opposite over hypotenuse. So 1 over 2. We end up with square root 3 over 2. What am I doing? No, I'm messing that up. I'm sorry. Sine of pi over 3 is actually square root 3 over 2. I was using the wrong angle. Opposite over hypotenuse. So we end up with 3 over 2. Cosine of pi over 3 is adjacent over hypotenuse. So this is 1 over 1/2 minus 1/2. 1 divided by 1/2 is 2, minus 1/2, so we end up with our 3 over 2. So we have shown this to be true for the angle pi over 3. We haven't shown it to be true for any other angles, but we have shown it for pi over 3. Just going to bring up my calculator here. Now, for the second way is to use it to see if it's the case on our calculator. So we are going to check to see if our calculator shows that this could also be an identity. So 1 divided by cos x minus cos x, that is my left-hand side. My right-hand side is sin x tan x. And I have the colors here. I'm going to go zoom trig, which is 7. Hit enter. And here is the graph for the first one. And you can see quickly that you have an overlap with the second one. So that's the verifying over a larger domain. That's verifying between between negative 2 pi and 2 pi. Yeah, it's an identity because we have the overlap, but we still haven't proved it. We have just shown it to be true for the questions from negative 2 pi to 2 pi. So it's not proved yet, it's only probable. I cannot give instructions on how to do this step by step. You have to develop a feel for this. The first thing that I'm going to suggest is you take the more complex side. In this case, it's the most complex side because we have a fraction subtracting a trig function. Over here, we just have 2 trig functions multiplied together. So the left-hand side is the most complicated. I look at this and I see I've got a fraction. I'm going to try to see if I can get rid of that fraction or write that fraction in a better form. So I'm going to write this with a common denominator. So I'm multiplying this guy by cos x over cos x, which is 1. So I haven't changed this at all. I've multiplied something by 1. I now am able to write this over a single denominator. So I'm getting close. The 1 minus cos squared x is very familiar. This guy here, I subtract cos squared x from both sides, and I end up with this. So I can take that, what I've seen on that other page, and replace it with sine squared x. So I'm simplifying 2 terms down to 1 term. This entire thing is sine squared x. I'm going to replace that. I'm not quite done yet. I'm going to write the sine squared x as sine x times sine x. And then I'm going to put this guy over cosine x. This is our quotient identity for tangent. And we have shown that to be true for everything. The last step is to check to see what values this doesn't work for. It works for all, this is an identity for all values inside its domain. But there are some values in this identity here that are not in the domain. One, we have cosine x on the bottom of a fraction. We can't have that. And we have tangent x, which has built-in restrictions. It has non-permissible values itself. So cosine x equals to 0 when x is equal to pi over 2 plus pi m. So cosine is 0 there and there. Sine is just at pi n. Sine is equal to 0 here and here. Tangent is equal to 0 when sine is equal to 0, because we have sine x over cos x, so again we have pi n. And cotangent x is equal to 0 when cosine is equal to 0, which is here and here. So we have pi over 2 plus pi n. Now those are, you don't have to memorize them. I have these things that I use. The other thing that you have to remember is, as I said, there's some non-permissible values for tangent, cotangent, secant, and cosecant. So tangent and secant are undefined when cosine is equal to 0, so we're undefined at those 2 points, pi over 2 and 3 pi over 2. Cotangent and cosecant are undefined when sine is equal to 0. And so at those 2 points. Once we keep this in mind, we can find our non-permissible values fairly simply. We cannot have 0 on the bottom of the fraction, and then we also have to look for everything that has built-in restrictions, which is everything but sine and cosine. So we have tangent. Tangent is undefined here and here at pi over 2, 3 pi over 2, and all the multiples of it. We have cosine x cannot equal to 0 because 1 over 0 is undefined. So cosine x cannot equal to 0. Cosine x is here and here. So our looking at this, the identity or the non-permissible values are x cannot equal to pi over 2 plus pi n, okay, where n is an integer. Again, so we're pi units away from the next guy. Each guy is pi. So we just need to add pi to get to the next stage. The next question, we're going to again use a special triangle angle, 45 degrees. So we want to see is if this identity, this statement, sine of 45 times cosine of 45 squared plus the sine of 45 cubed, if that is equal to 1 over cosecant of 45 degrees. Using my special triangle, sine of 45 is square root 2 over 2, cosine square root 2 over 2 squared, and then we have square root 2 over 2 cubed. Cosecant is hypotenuse over opposite, so 1 over 2 over square root 2. This works out to be square root 2 over 2. Now here we have square root 2 squared, that's 2. So our top is 2 square root 2. We have 2 times 2 squared, so that's over 8. Over here, 2 square root of 2 cubed is 2 square root 2 over 8. We have 4 square roots of 2 over 8. Reduce that to square root 2 over 2. So the statement is true for 45. I'll leave you to graph that one on your own. So to prove this, how do we prove it? Well, generally, I look for Pythagorean identities first. I look for these. Yes, I have some in there, but it's going to make it more complicated. It's going to blow stuff up. The next thing I look for is can I factor? Well, in this case, I can factor. I have a common factor of sine x. Taking out a sine x, that leaves me with cos squared x plus sine squared x. Going back to my Pythagorean identities, I have a perfect one right here. That's this one. I see sine squared x plus cos squared x. Every place I see that, I can replace it with 1. So I get to replace this entire bracket with 1. Leaves me with sine x. Alright, well, I'm going to take this guy here. The reciprocal of cosecant is sine. So now we have shown that they're true for every number. This one only showed it was true for 45 degrees. This one only showed it was true for negative 2 pi, because that's what I would graph this at. Here are some hints. As I said, begin with the more complex side. Leave the least complex side alone. Look for your Pythagorean identities. These 3 identities and their modifications. Then look to factor. Most often we're either going to do a difference of squares factoring or a common factor. Not often are we going to go to ask you to do other factor. If that doesn't work, go ahead and what I call the brute force method, turn everything into sine and cosine and perform the algebra on it. In this situation here, I am going to turn everything into sine and cosine. I will do that to both sides. So 1 over cotangent, this becomes 1 over cosine over sine, which is sine over cosine. Over here, that's in sine, that's in cos. Tangent, okay, I'll deal with the tangent. So I'm going to do a little bit of modification. I got sine x plus sine x over cos x. And instead of writing this on the bottom, I'm going to multiply by the reciprocal. Just to tidy this up, it's not the worst thing in the world to leave it as it was, but multiply by the reciprocal. That's the same as dividing by a fraction. This is cos 1 plus cos x over 1, hence its reciprocal. Now this here, I need a common factor to add these together. A common denominator. My common denominator is cosine. So I'm going to multiply this term here by cosine x over cosine x. I'm going to leave this guy alone. And this guy over here is just going to be coming along for the ride. Tidying up a little bit. I see a common factor. I'm going to take out that common factor of sine x, leaving me with cos x plus 1. That's all over cos x. And then over here, I have 1 plus cos x. Now, I see this. I have cos x plus 1, I have 1 plus cos x. They're the same because they're both positive, so they get to be crossed off, leaving me with sine x over cos x, which is exactly what I have on the right-hand side. The non-permissible values, we need to go back to here. We have tangent x, we have cotangent x, which have built-in non-permissibles, and then we have 1 plus cos x cannot equal to 0 because it's on the bottom of a fraction. So cos x cannot equal to -1. Cos x cannot equal to -1 at that spot there. Now we also have tangent is undefined. Tangent is always undefined at those two spots. And cotangent is always undefined at those two spots. So what we have here is an angle of 90 degrees between each of these. So our non-permissible values, x cannot equal to pi over 2 n, where n is an input. So every 90 degrees, we have a non-permissible value for this identity. Now, I'd like you to stop here and do this question. I'm going to do it right away, but stop, try it on your own, and then come back and watch. So, the only way I see this is turning that guy cosecant into sine. And again, I'm going to multiply this by 1 minus sine x. It's just a little tidier in this case. Now we can't cross off anything yet. This guy is not over 1 denominator. So we have 1 over sine x minus sine x over sine x. We still have that guy here. Writing it over 1 denominator. Now you can see that you have this and this. Leaves us with 1 over sine x. Those can cross off because they're the same. 1 over sine x is cosecant x. The non-permissible values, we have that guy, 1 minus sine x cannot equal to 0. Because it's on the bottom of a fraction. Sine x cannot equal to 1. We have cosecant. We know cosecant is undefined at those 2 points. And then this guy can't equal, so we have 3 points to deal with. We have 2 equations. X cannot equal to pi n, and x cannot equal to pi over 2 plus 2 pi. Where n is negative. So pause again. I'm going to do the next one here. I don't really see a way I could substitute things in for each one of those, but I don't think it really helps me. So I am going to basically brute force this. I'm going to take my tangent, write it as sine squared x over cos squared x. Since tangent is equal to sine x over cos x, tangent squared will be equal to sine squared over cos squared. Now you can see by doing that, those two are going to cancel each other off. going to be left with sine squared x plus sine squared x. That gives me 2 sine x. Now, I could write sine x as 1 over, sorry, I need a square there, 1 over cosecant squared x, which is what we have over here. The non-permissible values from this, is coming from this guy and this guy. Well, this one here I'm going to say you can ignore, because yes, cosecant squared x can't equal to 0 in this expression, but cosecant squared x can never equal to 0. So that guy will never equal to 0, so we don't have to worry about it. We just have our tangent, which we know to be undefined at those 2 points. So x cannot equal to pi over 2 plus pi n. So please pause and do the third one. The more complex side is this guy. There are a couple ways of doing this. Again, I don't really see any way other than turning this into cosecant into 1 over sine. One of the ways is to multiply this in. So using our distributive property, we end up with sine x over sine x minus sine x. Sine x, something divided by itself, is 1. And therefore, now they're equal to each other. The non-permissible values, the only place that comes from is cosecant. Cosecant is undefined, where sine is equal to 0. Those 2 places there. So x cannot equal to pi n, or n is all of the Pause and do the third one, or the fourth one, I should say. Again, we are doing this with straight brute force. I'm going to write cosine x minus cos x over sine x. And for timeliness sake, I'm going to multiply it by 1 over 1 minus sine x. Just because it avoids that fraction over a fraction. Leave this guy alone for now. Here, I need a common denominator to subtract them. So this becomes sine x cos x over sine x minus cos x over sine x times 1 over 1 minus sine x. Tidy this up a little bit. Sine x cos x minus cos x all over sine x. Bring this guy along for the ride for the moment. What we see here is I have a common factor of cosine. Take that guy out. It's going to leave me with sine x minus 1. Now, at this point, I look over here, I have 1 minus sine x on the bottom. I'd like to be able to cross that off. I can't do this because this is positive sine, that's negative sine, that's negative 1, that's positive 1. So if I take out a negative cosine, the sign changes there to negative, changes there to positive. And I'm left with, I still have my sine x on the bottom. Now I have 1 minus sine x and 1 minus sine x. Those guys are going to cross off. And I'm left with negative cosine x over sine x, which is negative cotangent x, which is what we have at the top. The non-permissible values have to do with cotangent. He shows up twice. And then I have the non-permissible values from the 1 minus sine x. 1 minus sine x cannot equal to 0. Sine x not equal to 1. That occurs here and here. And then we also have cotangent. Cotangent is undefined, where sine is equal to 0, which is here and here. Looking at that, every one of my non-permissible values are pi over 2 units apart. So x cannot equal to pi over 2 n, where n is all integers. Now we can also think about this as 0 plus pi over 2n, but I just leave out the zeros. So you have the homework on this page. You have my notes on this. The homework was here. Try those questions. I will go over this again tomorrow.